Hello and welcome to this video on lists and data structures and algorithms. In this video we will look at lists, which are one of the most fundamental data structures. Today we will explore different types of lists, their operations, and we'll also quickly discuss what arrays, stacks and queues are. A list is a linear data structure that stores elements in a sequence. Unlike arrays, lists are dynamic, meaning they can grow or shrink as needed. So we can add or remove elements from our list. In linked lists, each element, also called a node, contains a value and a reference to the next node. This makes lists very flexible and efficient in certain use cases. Lists can either be implemented as an array or as a linked list. If you know Java, you might know the array list and the linked list. But what is an array? An array is a collection of items. It is a static data structure, meaning it cannot grow or shrink during the runtime. So if we want to add an element, we have to copy the entire array into a new one. That is very complex, but an advantage of arrays is that we can easily access an element directly by using its index. This makes it very fast, especially for reading. So an array would look like this. We have different fields for our elements, and each element has an index. The first element, like in a list, is always 0. So in this case, the element at the index 0 is 7. And we have the element 2 at the index 1, and so on till our last element, which is the element 1 at the index 4. So we can see, unlike in a list, the elements are not connected. So for example, if we want to do with our last element, we don't have to iterate over the entire array to access it, but we can easily access it by its index. Then there's also another implementation variant called the linked list. There are different types of linked lists. On one hand, there's the singly linked list. In a singly linked list, each node contains two parts. One part stores a data value and the other part stores a pointer to the next node in the list. The list begins with a reference called head, which points to the first node. In this case, our first node is the node that contains the value Marie. Then the second node contains the value Alice, and the third node contains the value Leo. Also, the last node points to null, which basically indicates us the end of the list. On the other hand, there's the doubly linked list. In a doubly linked list, each node has a reference to the next node and the previous node, which allows easier traversal. So the list begins with the reference called head, which points to the first node. Additionally, we have a reference called tail, which points to the last node. So we can either traverse from the head to the tail or from the tail to the head. So what are the operations we can do on linked lists? For the operations on singly linked lists, we basically have insertion, deletion and searching, either at the beginning of the list, at the end of the list, or at a specific index. All operations at the beginning of the list have a time complexity of big O of 1, because for example, if we want to add an element at the beginning of the list, we just have to insert it at the beginning of the list and change the pointer of the head to the new node. If we want to delete an element at the beginning of the list, we can just delete it, and then we can update the pointer of the head to the next node. So if we would delete the node with Marie, the new head element would be Alice. And of course, if we want to return our first element, we also have a running time of 1. But all operations at the end of the list have a time complexity of big O of n, because we have to iterate over all items in our list to get to the end, and then we can execute the operation we want. And for example, if we want to insert an element in the middle of the list, we also have a time complexity of big O of n, because we have a running time of n divided by 2 to get to the middle of the list, but we do not consider constants in the big O notation, which leads to a time complexity of big O of n. Also, if we want to traverse through our singly linked list, we also have a time complexity of big O of n. For the doubly linked list, all operations at the beginning or at the end of the list have a time complexity of big O of 1, because if we want to execute an operation at the beginning of the list, we can just start at the head, and if we want to execute an operation at the end of the list, we can start at the tail. Operations in the middle of the list also have a time complexity of big O of n, because no matter if we start from the head or the tail, we have a running time of n divided by 2. And an array, on the other hand, is, like I said, very efficient for reading. So we can access every element by its index in big O of 1, but every other operation is similar to the linked list, because it has a worst case time complexity of big O of n. If we search for an element, we have a worst case running time of n and a best case running time of 1, but if we want to insert or delete an element, we have to copy the entire array into a new array in big O of n, and then we can execute the operation. Another useful data structure is the stack. A stack is a simple data structure that works based on the last in, first out principle. This means that the last element we put in is the first one that comes out. You can only interact with the top of the stack, so you can add an element at the top of the stack, which is called push, and if we want to return the element at the top, we can use peek. A good example is a stack of books. You can only add or take the top book. And there's also the queue. Unlike stacks, queues work on the first in, first out principle. The first element that goes in is the first one that comes out. So you can add an item to the rear of the queue with the operation enqueue, and remove the item from the front with the operation dequeue. We can also return the item from the front with the operation peek. You can think of a queue like a line in the supermarket checkout. The first person to arrive is served first. Both stacks and queues are abstract data structures and they can be implemented in different ways, most commonly using arrays or linked lists, and each approach has its pros and cons in terms of memory usage and performance. In the next video we'll look at some sorting algorithms. Thanks for watching and see you there.